Okay, we are now in section 12.4, double integrals in polar coordinates. So, all right, how many remember polar coordinates from Calculus 2? Okay, Alexander remembers, and Simon remembers, and Angela, absolutely. So, well, in section 12.3, you did double integrals with respect to Cartesian coordinates, x, y coordinates. But sometimes it's more convenient to use polar coordinates to compute a double integral. So how does this work? How does this work? Well, let's go down here a little bit. So you see in figure one here, you have a couple of situations in which integration using like if you're like in figure one, if your region is x squared plus y squared equals 1, okay, and you wanted to do a double integral, Cartesian coordinates could be a little messy. So let me show you why here. Let me show you why. Okay, so I'm just drawing. Put that there. Okay, one moment. Okay, I'm going to draw that a circle. Not a perfect circle, I know. All right, and this circle is, say, x squared plus y squared equals 1. Now, say this is your region D. In section 12.4, they call it region R, but let's just call it region D. And this is 0.10. Okay. And maybe you have a function. Okay, I want to be careful here. A function f of x, y. That's like x times y. Let's just say. And you are doing this integral. And you're going to do dy dx. So what would the limits be for for our circle? Again, this is our circle. So well, what you have to do is you have to consider the top half of the circle, and you have to consider the bottom half of the circle. Here's the bottom half of the circle. Now for the bottom half of the circle, what's y equal to? And for the top half of the circle, what's y equal to? Can you tell me? What I'm trying to do is figure out limits for y. I'm integrating with respect to y first. That's good. That's good, Norina. The bottom part is y equals negative square root of x squared minus 1, because if you take x squared plus y equals 1 and solve it for y, you're going to get y equals plus or minus the square root of, 1 minus x squared. Yes, that's right. So it always is good to show work. If you don't show work, it's easy to make a mistake. Right, so this is 1 minus x squared. And then that's negative, right? Man, come on now. Let's get our negatives drawn properly. And then on top, you have y equals positive square root of 1 minus x squared. So the limits then, the limits now are negative, the y limits go from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And then what would the x limits go from, class? What would the x limits go from? Here and here. Any coordinate in here, the x coordinate would go, that's right, Mary, good, from negative 1 to 1. And this is an acceptable, I mean, this is like if you were trying to find like the volume of between this surface, f of xy equals xy, and the xy plane over this region D, the volume would be this double integral. But where does the complication come in to? Where does the complication, what might make this double integral complicated? What do you see in this double integral? Well, okay, I mean there are things, but there's something I'm looking for. If you look at this entire this entire integral here, and you know you want to get to the end, you want to get to an answer. What might make it a little hard to do the integration eventually? Okay, well, I guess I want to be a little careful here, but clearly the square roots, the square root terms can be a concern. I mean, usually I mean, it's not like we can't manage it if it comes up, because we could, you know, perhaps like we would need to use, I mean, I'm just saying, I don't know, I haven't worked this problem out, but sometimes when you have a square root, you need to use a substitution, right? So if you do the inner integral here, well, I'm just sort of making up an example, and it might be that I guess here the square roots would go away on the inner integral. But I'm just saying, when you have limits that involve square roots, it can make life a little more difficult for you when you do your integration. And so and like when you deal with like circles, okay, circles. So if you're going to use the section 12.3 approach, you got to take that circular region and break it up into a top and bottom function. Okay, and that's fine. But with the square roots there, as your limits, it can make things a little more difficult. And so we resort to polar coordinates in certain situations like that. And the situations where we can see this is like what you see here. And I just showed you why there in figure 1. So, okay, polar coordinates. I don't think we need to review it, but as you know, if we have an integral with respect to, if we want to convert, I want to say this the right way, we have our conversion equations for taking us from rectangular coordinates to polar coordinates and polar coordinates to rectangular coordinates. Now, what would a double integral look like? How would a double integral work? Well, without getting too complicated, in the region that you're working with is called a polar region. So they use R, but it's really a D, a region D. And in terms of like circles and angles and radii, region R in this figure 3 is bounded between the angles theta equals alpha and theta equals beta. And the radius goes from R equals A to R equals B. So what you can do is you can take the, and again, you know, this, so like if you were integrating over a rectangle, okay, this polar coordinates would not be a good choice, right? But if your region D looked like this, some kind of circular looking thing, it could be helpful. So, okay. Well, we take our polar region R and we divide it into polar subrectangles. So every polar subrectangle has, there's a, I want to say it the right way. So you see there that R sub ij, that polar rectangle, or subrectangle I should say, goes from one angle theta equals theta j minus 1 to an angle theta equals theta j. And then there's a beginning radius, R sub I minus 1, and an ending radius, R sub I. Okay, now what we can do, let me take off my my email here. I don't want to be disturbed. Okay, so how would we then do an integral, not with respect, a double integral, not with respect to Cartesian coordinates x and y, but polar coordinates r and theta? How would we do this? Well, the best way, I mean, here's how I will think about it. Here's how I like to think about it. Now, the book goes into some detail in terms of a derivation, but I'm going to keep things simple here. I'm going to keep things simple. So, okay, I mean, here's what we are used to. Okay, so we could have dy dx or dx dy over a region D. This is what we're used to. This is, let me just try to be, you know, or dx dy. This is section 12.3. So how would we adapt that double integral with polar coordinates? Well, okay, we'll call region D region R. And x I'm going to replace with r cosine theta, because x equals r times the radius times cosine of theta. And y, so, you know, here's x, here's y. Y I'm going to replace with r times the sine of theta. So for a function of x and y, I can write that as a function of r and theta quite easily. Now, what about this part here? What about the dy dx, also known as the dA? Well, remember, dA is equal to, it's not equal, it's a differential, but remember in section 12.1, when you were learning about, you know, what, like a double integral, how do you approximate a double integral using areas of volumes of boxes? You know, you had like heights times delta A times the area of the subrectangle. So can I somehow think of delta A in terms of the polar coordinates? And you can. here's how you do it. Here's how you do it. So remember, in the picture here, let's just take a look at one of those polar subrectangles. Okay, that is has a starting angle and an ending angle, which are pretty close together, and a starting radius and an ending radius, which are pretty close together. Okay, if we look at that, like they show in Figure 5 here. So remember, you can make the subrectangles smaller and smaller. And that was done by having the starting and ending angles closer together. Okay, and then the radii can be closer also. So what happens is that area of the polar subrectangle, basically the dA part. So the change in radius is dr, or delta r, and the change in the angle, it can be approximated, well, d theta is your change in angles, and for the length of an arc, or if you think about the sector of a circle, sector of a circle is equal to the radius times the difference in the angles. Okay, so I want to say this the right way. One moment here. One moment. Yeah, so like for example, I really don't want to change that. Hold on. If you have okay, so if you think about, I'll just do, I got to fit this in somewhere. Try to fit it in down here. So, you know, maybe you have a circle with radius 2. What's the circumference of the circle? What's the formula for circumference? Well, that's 2 pi r, right? 2 pi r. So that's 2 pi times 2. So that would be the entire circumference of that circle. But if you wanted just a quarter of the circle, okay, that length for the quarter, for the, you know, 1/4 of the circle, is going to equal just, it's, well, this is 4 pi. What's the length for 1/4 of the circle going to equal? If the circumference of the whole circle is 4 pi, for 1/4 of the circle, what would the length be? That's right, Norina, it would be pi. And so that's like taking, I want to say this the right way, that's like taking 2 times pi over 2, because this angle here is pi over 2. So that's like r times the change in the angle. Okay, and so when we go back to the picture here, and that equals pi, right? 2 times pi over 2 equals pi. Let me just put that in just so. Okay, so Okay, so in the, hold on here, got to make sure you're seeing what I'm seeing. So you see there for the figure 5, that area, I mean that little polar subrectangle almost looks like the area of a box. And basically, think about the area of a box. How would you find the area of the box? You would take width times height. Well, the width is equal to the change in the radius, and the height is equal to the length of that little arc, which is r times d theta. You see that? So r d theta times dr is the area of that polar subrectangle. And so now going back to what we were looking at, okay, if we are then going to put in dA here, it's going to be r dr d theta. And so now we have the equivalent double integral in polar coordinates. So if we change the polar coordinates in the double integral, this is going to be what the double integral is. And now that is supported, of course, by this formula here. And of course, you'll have access to this formula on your exam. As you know, you can access the ebook on the test. But of course, it's easier just to remember the formula. But now at least, do you understand how that came about? It's sort of an intuitive derivation. An intuitive derivation. All right. So what I want to do, I'd like to do just one example, and then I'm going to set you on break. We're going to do multiple examples, but I want to do at least one before I set you off on break. So let me bring that example up here. Let's do this example here. Okay, so take a moment to copy the example down. Please let me know if you have any questions. Okay, so of course, I'm going to let you keep copying. We want to find the volume of this solid. Now, I'll just mention, you might have learned in Calculus 2 how to find volumes, but in Calculus 2, the only way you could find a volume usually was by rotating a function about some axis. And then you had like washers and shells and all that. But with double integrals, we have a much more a way to compute volumes that's much more, that can be used in a wider variety of situations. Okay. And we know finding the volume, we're going to compute some double integral. And the solid is bounded between the plane z equals 0 and this paraboloid. Now, does this paraboloid, z equals 1 minus x squared minus y squared, does that open upward or downward? Because we gotta know, we gotta have a picture of what's going on here with this paraboloid. Is it so a bowl? Paraboloid is a bowl shape, right? It has a bowl shape. Does the bowl open upward or down? That's right. That's right, Norina. That's right, Lexi. It opens downward. And what's the highest point on the bowl? So I'll just mention it. That's right, Lexi. 1. So very good. So if z were equal to x squared plus y squared, that bowl would start at the origin and it would move upward. But that's not what we have here. We have z equals 1 minus x squared minus y squared, which it can be written as 1 minus the sum of x squared plus y squared. Okay, so think of it like this. Think of it like this. So if you had z equals negative x squared plus y squared, this bowl or paraboloid, does it open downward or upward? Z equals negative quantity x squared plus y squared. Does the bowl open up or down? Well, if z were equal to positive x squared plus y squared, does that bowl open up or down? Bowl is a paraboloid. When I say bowl, I mean paraboloid. Good, Mary. That bowl opens up. So now, if I put a negative here, what's that going to do to the bowl? Does the bowl open up or down? So, you know, this is bowl 1, opens up. Bowl 2, z equals negative x squared plus y squared. How does that open? What's the effect of putting a negative in front of the x squared plus y squared? What does it do to the bowl? How does it affect the opening? That's right, Norina. It has to open down. It has to open down. Now, for the third bowl, which is the paraboloid that we're talking about. See, I'm trying to give you a little training here so that you're comfortable. Well, okay, we have a 1 minus x squared, 1 minus the quantity x squared plus y squared. So it looks like we have a bowl that's opening downward, but what's the effect of the 1 there? What does the 1 do? What does the 1 do to the bowl? Yeah, does it raise the bowl or lower the bowl? So, you know, let me just see here. I guess here's for bowl number 1, z equals x squared plus y squared, opens upward from the origin. Bowl number 2, z equals negative quantity x squared plus y squared. That opens downward from the origin. And now we're on bowl number 3. If we were to draw bowl number 3, it's going to open downward. But what's the high point going to be? Right, it moves it up 1 unit. That's right. So that's right, Lexi. So this point here is going to be 0, 0, 1. Okay, I'm just trying to. I mean, we gotta be comfortable. I want to be sure you're comfortable with that. So bowl 3. Here's bowl 3. It opens downward. The paraboloid opens downward, and the apex or high point is 0, 0, 1. Please give me a thumbs up if you're comfortable with this, because paraboloids, you're going to see those a lot, right? You're going to see those a lot. Good. Matthew's good. Mary's good. Yeva's good. Angela's good. Angela's good. Narina. Are there any questions? All right. Logan's good. Wonderful. Wonderful. All right. Well, here's the next question for you. The paraboloid opens downward. Z equals 1 minus x squared minus y squared opens downward. And we know the volume of the solid is the volume of the paraboloid. Well, it's bounded between z equals 0, that's the xy plane, and so you have a downward bowl, and it's going to touch the xy plane. We want to find the volume of that solid, the solid bounded above by our paraboloid and below by the xy plane, which is z equals 0. So, as you know, it's important to understand what the intersection is between the plane z equals 0 and the paraboloid. The paraboloid would intersect the plane in what? What would the intersection look like? That's right, Simon. It's going to be a circle. Ah, a circle. Well, and that means the region D is a circle. So in that situation, polar coordinates might be very helpful. Okay, so if I go to the next page here, here's a little detail. Let me give you a moment to copy here. What I'm doing is I'm drawing the bowl, the downward bowl, the paraboloid, and then region D, and I'm first writing the volume, okay, of this solid. I'm writing it in with Cartesian coordinates. Okay, and clearly the bowl intersects, the paraboloid intersects the plane in a circle with radius 1. So I'm going to let you copy to here. Please let me know if you have any questions before then we continue. We're going to then continue on. And while you're copying, I'm going to ask Mary and Abby. Can you hear me okay, Mary and Abby?
Yes.
Good, good. And Abby? Okay. Yeah, Mary, can I just chat with you just a moment during the break? Just like I needed to mention something to you. It'll only take a few, just like a minute. Does that sound good?
Yeah.
Okay, very good. Thank you. Thank you. Okay, so now could this computing the volume using Cartesian coordinates, could you do it? Could you do it? Well, you can get the antiderivative with respect to y of this integrand, but I think the resulting integral, when you put in these square root limits, it's going to be a little bit complicated. I'm not saying you can't work, but it's certainly going to be a little complicated. So, being that the paraboloid intersects the plane in a circle, how do we know that? Well, intuitively we know that when a bowl, I'm sure how many have like taken a bowl and maybe it's wet on the bottom and you put it on, I don't know, the counter or something, and when you lift the bowl up, it leaves like a ring. How many maybe like a ring of water? How many maybe have noticed that? Yeah, Mary has, and Norina. So intuitively, we know that it's the intersection is a circle between the paraboloid and the plane. And we also know that where the paraboloid and the plane intersect, both equations have to be true, meaning 0 is equal to 1 minus x squared minus y squared, which means that x squared plus y equals 1. So, now we know we know the limits here then based on the picture, and we know this double integral is correct, but now we have to compute it. And with Cartesian coordinates, it could be a little complicated. Being that double integral is not easy to evaluate. So let's try to use polar coordinates. So, okay, the circle with radius 1, radius goes from 0, let me maybe use goes from 0 to 1. And theta goes from 0 to 2 pi. Those are your limits. The 1 minus x squared minus y squared, remember, 1 minus x squared minus y squared is like 1 minus the quantity x squared plus y squared. And so you get 1 minus r squared for your integrand. And then the dA is r dr d theta. Now, what do you notice about these limits? The limits in the integral with respect to polar coordinates. What do you notice about those 4 limits? They are all what? They are all yeah, they're all integers, they're all numbers, they're all constants. That's right, Mary. So remember, when you have that situation, Fubini's theorem can be used, but Fubini's theorem may not be, well, it isn't really necessary here. But the point is, the constant limits are a little easier to deal with than functional limits. So let's see what this does for us. All right, I'm going to go to the next page if we're good. Are there any questions? Okay, let me go to the next page. Okay, so I'm just doing a standard integration here, but I want to show you something. So this here, this integral, which is the integral from 0 to 2 pi, integral from 0 to 1 of r minus r cubed dr d theta. Well, no, I'm gonna show you this later. I'm gonna show you this later. Let me just let you copy it. Okay, so yeah, easy to get the antiderivative of r minus r cubed, and now you have a calculus 1 problem, and you go forth and you get the answer, and the answer is pi over 2. I'll give you a moment to copy it down. I want to show you one thing in the whiteboard as well. All right, one moment. Excellent. So Abby, can you, so people are copying. Abby, can you hear me okay?
Yeah, I can hear you.
Excellent. Hey, I want to talk to you and Mary just for a moment right after the break. It's nothing, you know, everything's fine, but I had to mention something to you both. It'll only take me a moment. Nothing bad, okay? All right?
Yeah, you got it.
All right, excellent, excellent. So are there any questions on this, this on this, what we did? I think you agree that it's much easier to use polar coordinates in this case. So how many are feeling reasonably good so far with section 12.4? Okay, Yeva's good. Noreena's good. Logan's good. All right, wonderful. And Sadana's good, good. And hold on, there's another person there. Hold on. Mary's good, Logan's good. All right. Samuel's good. Okay, so let me show you something here. Let me go to the whiteboard real quick. I want to just show you something on that integral, that double integral, I should say. All right, so let me clear this. Okay, so okay, so here's the iteration. And what can you tell me about this inside integral? Should put parentheses here, right? That integral is a what? I'll give you a hint. First letter C, second letter O, third letter N, Yeva, fourth letter S. That's right, Mary, that's right, the constant. I mean, I mean, it is a constant. And so because of that, you see, you could pull that inner integral out of the, out from the outer integral here. You can pull that inner integral out. And now, can you do this all the time? No. See that? How many would maybe try to do the integration that way? Okay, so yeah, we did it a few times. So I'm just saying, sometimes there are, I mean, and then you have two very simple integrals and you just compute each one and multiply. So sometimes there are, students can do integration. Sometimes there are several ways to do the integration. And in this case, you could do it this way. Okay. And so, you would work out this integral and then multiply, and that would turn out to be that is 1/4, right? And then the second integral, it will turn out to be, when you work it out, 2 pi, and 1/4 times 2 pi is pi over 2. So, all right, are there any questions before I stop the recording? We'll do more section 12.4 examples after the break. Okay, great, great.